So for our final talk this afternoon, we have Griffin Wang, and we'll hear about Hitchin-type fibrations.
Thanks for the introduction. So the title is on Hitchin-type fibrations, and it's a non-introduction because it's more of an introduction to introduction. Okay, let's get started. So the talk is split into three parts. So first, I like to talk about Griffin sum. So let K be a finite field with P elements. So as an additive group, it's just sigma PZ. And let psi be a character on K. So for example, this exponential here. And I fix a point in non-zero element K, so K cross. And the Griffin sum associated with psi and A is defined to be this summation. So the summation is over the non-zero element of K. This is a self written. This is self convolution psi with this so at A. Okay, and for later purposes, I like to rewrite it in a more symmetric way. So you can see it's just I introduce xy equals A, and I have this summation here. Pretty simple. And we also have a twisted version of Griffin sum. So K prime over K, a quadratic extension, and its Galois group is generated by sigma. This is the Frobenius element. So the twisted Griffin sum associated with the psi and A, so we'll still keep the psi and A, and it's written this way. And instead of explaining the terms in the summation, I like just to rewrite things. So if you're not familiar with the finite field at all, you can just pretend this K is real numbers and K prime is C, and the sigma Z is just a complex conjugation of Z, except there are finite many Z's, so summation will make sense. So the Griffin sum is just this summation over this hyperbola defined by A, and the twisted one is just this circle defined by A. So quite similar summations. And they have a very interesting relation with each other, which is called Haas-Davenport identity. So for any A and any psi, we have this identity between the twisted and non-twisted Griffin sum. They differ by a negative sign. Okay. And I like to interpret this problem in a geometric way. So the Griffin sum, if we look at the definition, rewritten a bit, it's just counting K solutions to the equation xy equals A. Okay, but we're not literally counting. We weight every point by this psi x plus y function. So the weighted point counting. So if you define this Ka to be this on two-dimensional plane, and cut out a variety cut out by xy equals A, then the K solutions to this equation is the same as the Frobenius or Galois fixed point of this variety. So basically, to summarize, Griffin sum is counting a Galois fixed point of a certain variety defined by A, weighted by the function psi x plus y. And similarly, we have tau, the involution xy to yx, and the Griffin sum, twisted Griffin sum can be interpreted as a similar point counting problem, but the sigma action is composed with sigma with tau, so it's a different action. They differ by tau. Okay, keep this in mind. And now I introduce some tools from algebra geometry called Grothendieck-Lefschetz trace formula. So if X is an algebraic variety over K, a finite field K, then the fixed point of Frobenius of the variety, the number can be counted by computing the trace of Frobenius on the analytic cohomology with compact support. So in spirit, this analytic cohomology compact support is kind of like a singular compact supported cohomology on complex manifold. So a few remarks is this is basically an enhanced analog in the finite field case of the classical Lefschetz fixed point theorem. And it translates point counting problem to cohomological statements, some action on cohomology groups. And if we want to do weighted point counting, because Griffin sum and Griffin sum, they are weighted point counting, not literal point counting, you can just change the coefficient QR bar into some other sheaves through Grothendieck sheaf function dictionary. I won't go into details. So back to the Hasse-Davenport identity. To prove this identity between the Krusman sum and twisted version, we only have to show that this extra involution tau acts on the cohomology as -1. And here are some more details. I won't go through them now. If we have time, we can come back to this if anyone's interested. Okay, so beyond the basic example, let me present some higher rank examples. So first, the basic example itself can be reinterpreted using 2x2 matrices. So now let F be the field of Laurent series over K, and O be the ring of subring of a power series of K. And we have the residual map from F to K, which is just like the residual map of any Laurent series. Just take the coefficient in front of t to -1. In this way, the additive character of psi will induce composed with the residual map it will induce another character of F. And the last one is not so important. It's just later I'll introduce some integrals, and this is because the integral can be defined up to a constant scalar. So this is a way to normalize it. And then we have these matrix groups. So U and V are upper triangular and lower triangular matrices. So because it's 2x2, so U is basically just one parameter X, and V is one parameter Y. So as said, the additive groups, they're just isomorphic to the additive group of F. And A is this diagonal matrices alpha beta in F cross. So invertible diagonal matrices. And then we can also regard this psi F as character of U and V, where they're isomorphic to F. Okay. So we define this Krusman integral associated with psi and A. So A is a matrix 2x2 diagonal matrices. And I'll explain the details of this integral in the next slide. So let's just keep going. The important thing is there's also a twisted version. Okay, but I will not write down the detailed definition here. Just because knowing the non-twisted version is kind of you can see how the twisted version will go. Okay, let me explain the integral itself. So remember, reminder is that this U is an element of the big U, and V is in big V. So the integral is let me try to use this. The integral is over this U cross V group, so the variables are U and V. And this is characteristic function of 2x2 matrices with entries in O. And so it's really just when does this VAU lands in the 2x2 matrices with entries in O, and then they will contribute to the integral. So if you unpack the definition, you can write down a few stuff, and this is just some computation, algebra computations. And here I make an additional assumption that the valuation over F of alpha is 1, and valuation of alpha times beta is 0. Basically, the first non-trivial case. Then this VAU happens lands in this 2x2 matrices happens only if certain valuation conditions are satisfied, and you keep going. Eventually, you will reach the point such that this Krusman integral can be interpreted as it's the same as the Krusman sum. Okay, so Krusman sum here and the Krusman integral here in this special case. And for Krusman integrals, there is a similar identity, a generalization of Hasse-Davenport identity called Jacquet fundamental lemma that says the Krusman integral and its twisted version, which I never defined, they differ by a sign, except this sign is slightly more involved, not just -1. And it's proved by B.C. Ngo in 1999 in his PhD thesis. So he's my advisor. So this is true for any A and psi, non-trivial psi. And a remark is that there is actually a higher rank version, not just 2 by 2. So you can go n by n, and prove the theorem for all ranks. And back to the comparison between the Krusman sum and the Krusman integral, that we were seeing the first non-trivial case, the Jacobi fundamental lemma reduces to Heisenberg point identity. And the things will go very complicated if the valuations get large. For example, we have this comparison. If the valuation just one of them, just one more, then the summation gets much more complicated. So it's very hard to prove it by hand, but I heard people actually tried and succeeded. I think through some harmonic analysis stuff. But still, geometric solutions are very elegant, and actually there is a systematic way to interpret the Jacobi fundamental lemma into as identity of some closely related, like point counting on certain variety. And the geometric problem stems from this action, which is the U cross V to unipolar groups on the 2 by 2 matrix. So this is kind of the start of the thing. And this leads to the definition of Hitchin-type fibrations. And from what we're seeing in the Krusman case, we have this U, basically we are looking at this U cross V matrix groups acting on 2 by 2 matrices, but we don't have to restrict to this case. We can just consider an algebraic group G acting on variety N. For example, we have the classical example includes like G acting on its G algebra. This is the kind of classical Hitchin fibration. And also the adjoint action G on G itself, which is a multiplicative Hitchin fibration, which is my thesis. And we can consider like symmetrical pairs or like any like spherical variety and relatively trace formula cases stuff. And the starting point is basically always this this map from M mod G quotient stack to M mod G JIT quotient. There are a few difficulties associated with this method. If we just try to naively extend the Krusman sum case, which is first the geometric object. If the valuation or whatever gets really large, this Ka can be highly singular. So this Ka analog can be highly singular, but by itself is usually not that big of a problem because we can always do deformation and do some approximation. But another problem is a lot of times some interesting stuff is not of finite type, meaning like many tools in algebraic geometry are either underdeveloped or outright not available. And there are many other difficulties associated with different cases. So this is what really prompts the Hitchin-type fibrations. So this is so starting from this Ka, what we're really looking at is this this map of a stack of stacks. Basically, we can look at this O points. O is the ring of power series. So this Ka is basically the fiber of fibers of this map viewed as K spaces, and we may understand this as like O is power series. So basically germs of functions which relate to infinitesimal disks. So for any variety of stacks, so its O point is basically maps from infinitesimal disks to that variety of stack. Or if you are more classical, you can consider like contractible infinitesimal loops in this space. So this is kind of like a local, and to replace it with something global, we can consider a Riemann surface or algebraic curve rather than this infinitesimal disk. Okay, so we're considering instead of a map from this O to this space, we can consider a map from this C, the curve, to the stack and to the space. So this HC is the Hitchin-type fibration associated with the G acting on M. So the reason we want to study, the main reasons are twofold. First, this HC tends to have a much nicer property than HO. And second, because what we really care about is things about HO, not HC. But there is usually a way to deduce the result in the O point case from the C case. So from global, you can go back to local. So because of that, we were interested in it, and that will be the end of my talk.
Thank you. Questions?
What's the significance of Husterman sums?
You're asking the wrong person, because this is basically Husterman sum itself. I don't know the history, but for Jackie fundamental lemma, I think it's related to something GGP or some relative trace formula case. But for that, I don't personally know. Sorry. Yeah.
Is there general support here for the Hitchin-type morphism?
For the multiplicative Hitchin vibration, there a general support theorem you can sort of see a path to prove it, and specifically my thesis is about the multiplicative vibration, and there's a pretty precise support theorem of that.
Sorry, on your previous slide, you have this line saying one map is better than the other. Or is there some more precise statement?
So precise statement is that I think so basically, because previously we're looking at this Ka, which is the fiber of this map, right? And so the map itself is like a family of these fibers. So so this vibration itself is kind of already a deformation of this Ka, and this is like also a family. If you fix a specific fiber, then it's a deformation of that fiber. So globally, it seems, for example, you have, to be frank, like this, as I'm not sure if like even there is a good formulation of like arc stacks or so, and also this map itself is not like as written, so it's like pretty complicated if you want to add some trivialization and stuff to make it work. So what I can think of is like this map tends to be like not flat, and like the dimension can like jump pretty wildly, and this map is like flat proper a lot of time, or if it's not, in some cases it's like you can expect some smallness from it. So it's pretty reasonable to expect like the global case, where whatever it is you can kind of expect it's kind of an interpolation between smallness and kind of flat and proper. So you can hope to prove a lot of things about it, but the local case seems well, at least for I know there's no good result about like deforming the local family.
Also, what is the way to go from C to O?
So C to O is through the so-called product formula. So basically, so on a curve you have like infinite points, but only finitely many points are interesting. Like all the other points usually give you something trivial, like a 1 point, something like that. So basically, you can prove some sort of a product formula saying that the global fiber is a product of like finite many local fibers, while other points are just times the point. Yeah, so you can, usually what we do is like we prove something global, and you pick one special like local fiber and put it in the global family, but all other points are kind of simple cases, and you compute the simple cases and you can deduce one special local fiber. It's kind of like that.
Also here, C, you take compact curves, like proper curves?
Yeah, we take the proper curve, and also like this is also not exactly like what it should be, because it's proper curve. And for example, like if M is the algebra, it's affine. So from proper to affine, you really need some twist. So it's not literally what it is, but kind of close. Yeah. Yeah.
But there's some good classification what G acts on M has. Because in this general, probably it's too general.
So what
There's some like a good class of you expect a good.
I expect to have so from the results from my thesis, so this is kind of a thing I want to explore, which is just a general trace formula, how much of my method can extend to spherical varieties. So I expect a large class, for example, like symmetric spaces and stuff. We probably can kind of expect that. So instead of so traditionally we do the algebra case, and now we can just really do the group case.
Okay, it looks like we're done for the day. So thank you very much.